All right, here we are back in algebra again today, starting week 4. If you're wondering why my background is not the usual green Excel Center background, is because I'm using my personal laptop right now. I could not get my work laptop to even turn on all weekend. So, but I was checking assignments through Google. So I'm still behind with a few that I need to catch up on from you guys. So not to worry, I'll get to those today or tomorrow. And today we need to go do some more stuff with slope and actually start doing some graphing. Isn't that exciting? There we go. Okay, so hopefully you remember from last week how we started off talking about the different forms of equation. And that's hard to see. Why can't it be brighter? The different forms of equations: slope, intercept, point, slope, standard form, and then the slope equation that allows you to find the slope from 2 points. There's 4 or 5 different ways that we need to know how to find the slope. And so that's where we're going to start on today. And then we will go into some actual graphing in the different formats. So I think we talked a little bit about this last Thursday. But here's some of the ways that we got to be able to find slope. We need to be able to find slope when we see a line on a graph. We need to be able to find slope of a line when we have an equation. Anybody remember which forms of the equation give us the slope? Yep, the famous slope intercept equation, y equals mx plus b. Thank you. It's also in the point slope form. So wherever you see m, that's how you know you got the slope. Then we got to be able to find slope given 2 points, and just by doing a little calculation. Talked a lot about all the different ways that slope can be described. The vertical change over the horizontal change. We got rise over run. We got m. We got y2 minus y1 over x2 minus x1. They all refer to how steep or how flat a line is. And if you look in the definition, slope is the ratio of the vertical change to the horizontal change. So when you see that word ratio, that should tell you that you're looking at a fraction. And even if the slope is 5, for instance, as a whole number, I can still write that as a fraction, 5 over 1. Because as you'll see when we start graphing these things, we need both of those numbers in order to graph the line correctly. Rise and run, we need both of them. Looked at those. Now here's where we get into finding slope using a graph. And what you see on here is a line. Is it positive slope or negative slope? I hear one vote for negative. Anybody disagree?
Negative.
Another vote for negative. Anybody disagree? Everyone should be disagreeing, because that's positive slope. Up to the right is positive. It's that's not the line. The line is this fat orange thing here.
But I thought the little red arrow was pointing to stop on that red line.
It is, but that's not slope. That's just a point on the line.
Okay.
You see the box that's connected to that little red arrow? There's a gap. There's a gap here in the graph. It's a rectangular box. What this screen is suggesting is that you find the values, the ordered pair values for those 2 points, and then you do the calculation. Sure, you can do that. But why? Don't. That's too much work. Because if I start here at this point on the left and I start counting these squares, I'm going to go up 2 to get to this same level where the other point is. So I have a rise of 2. And from there, I'm going to count 1, 2, 3, 4, 5 to the right. So that's my run. Now I can find the slope as 2 over 5. Rise of 2, run of 5. I went up, so that's positive. I went to the right, that's positive. So my slope is positive, and it's 2 over 5. My rise and run is 2 over 5. That's the easiest way to find slope when you have a graph, because you can just count the squares. You know, this point here is at a particular level on the graph. The other point is at a different level. Different intersections allow you to just follow the lines of the graph and count the whole squares, the whole boxes, and that gives you rise and run. That's the easiest way to come up with anytime you have a graph. Because what they're showing down here at the bottom is to how to do the calculation. Because here they want you to fill in the ordered pairs for these 2 points and then do a calculation. Well, that's okay. Somebody want to give me this, the ordered pair for this one here on the right, on the line? X always comes first. So yeah, 2, 3. What about the one on the left? Good, -3, 1. Excellent. So this isn't going to be super accurate, but that's approximately where that point is. And over here's another one. So I got 2 points. This is why I'm suggesting to just count the squares instead of doing the calculation. Because our slope formula involves a little bit more work. Y from the second point, subtracting y from the first point. That's my rise. That's the change in y. And then below that is going to be x from the second point, subtracting x from the first point. Doesn't matter which one of these points you decide is the first point or the second point. And these x and y values are only good for labeling. So this, I'm just going to call this one the first point. So that's why we have x1, y1. That's just the first one that I see. And the second point, x2, y2. That's the second point. So now I can plug the numbers into the equation form. And the thing that gets a little bit tricky about the calculation, both the change in y and the change in x involve subtraction. So, and the only reason I'm drawing these boxes on here right now is to show you where the numbers get inserted. So on the top here would be y2 minus y1. On the bottom would be x2 minus x1. What's y2? y2 is 1. y1 is 3. x2 is -3, and I got to put that in there with its sign. x1 is 2. Okay, now you just do the calculation. 1 minus 3 is -2. -3 minus 2 is -5. Oh, they're both negative, which means they are positive. Negative divided by negative still gives you a positive result. But when we had the graph on here, it's just easier to count the squares. I know I made a mess of that, but if you got the graph, visually working with the graph is always going to be easier than trying to do the calculation, because since both of these equations here, this formula involves subtraction, if you leave out one minus sign, it's gonna be a mess. You're gonna get the wrong answer. So that's the risk. But if you concentrate when you have the graph to work with what you're seeing, that's for sure going to be easier. Another way that we have to be able to find slope, and here's another way that slope is described. It's described as a rate of change. Can you think of any examples in your life where rate of change is involved? I'm not talking about change from a 20. When you're driving your car down the road, what does the speedometer tell you? Okay, so what is the speed limit on the interstate? Not in Indiana, it's not 80. No, the legal speed limit. Say the whole thing. Miles per hour. You hear that word per there in the middle? That is a rate of change because it's comparing the miles per the hour. 70 miles per hour is a rate of change. So you use rate of change all the time in your life, you probably don't even know it. If you're involved in sports, you're going to come up with a batting average for baseball players. That's a kind of rate of change. Free throw percentage, those are in basketball. That's a rate of change. How many shots per attempt are they going to make? And so there's all kinds of statistical things that deal with the same idea. For this table example, they're talking about the change in distance and the change in time. So the first thing to recognize here with this table, this is just like a couple of columns out of a spreadsheet. Or if you were to draw a table on a Word document, you could tell it how many rows to put in there and how many columns to put in there. Whenever you see a set of data like this in a table, the first column is always the X values. The second column is always the Y values. Always, always, always. And that's kind of a fancier looking table than you might see me use in class, because a lot of time I'm just going to make what I would call a T chart. Looks like a T. All my X values go over here. All my Y values go in that column. And I can put as many little bits of data in here that I want, because they're in a relationship, and that relationship is based on the equation. So we can always calculate the change in y and the change in x when we have a table. One thing to look at is it a consistent rate of change? If you look in this x column, just go down through the numbers, +1, +1, +1, right? So the time is changing by a consistent amount. In the y column here under distance, it's going up by 260, 260, 260. So my rate of change here is 260 feet per minute. And that's what all this calculation stuff over here on the left is going to tell you. Because I could take any two of these numbers here in this column for distance. If I'm going to compare change in distance to the change in time, that's my change in y over the change in x. If I take 1040 and put it in this first box, minus 520, my value for the 1040 is 4. The time for 520 is 2. So 1040 minus 520 over 4 minus 2, that's going to give me 520 over 2. 520 divided by 2 is 260. Anytime we get a rate of change, what we're trying to get is this very last item had to have a denominator of 1. Feet per minute, per 1 minute, miles per hour, that sort of thing. It's basically a reducing fraction situation. So we can put any kind of data we want in these tables and come up with the rate of change if the changes are consistent. If they're not consistent, then we probably don't have what we're going to call a function where the y values are determined by an equation once you plug in the x value. So right there, I've talked about 3 different ways that we got to be able to find slope. From a graph, from 2 points, and from a table. Table just being a chart. Here's where that slope formula can come into play. And the thing I like about this particular slide is if you look at the graph over here, the change in y, it's exactly what I did on the earlier graph. Instead of doing the calculating, I counted the boxes. I went up and then I went over. Up's positive, to the right's positive. But I can do the same thing if I know the ordered pair at the beginning point and at the ending point. And that's what you use this calculation for. If all you have are 2 points and you're trying to find the slope, this is how you're going to do it. So let's see if we have an example here. We know about undefined and 0 slopes. Remember, there's 4 types of slope. Positive is up to the right, negative is up to the left. Undefined is a vertical line. It's not, the word is undefined. It's not indefinite. It's not infinite. It's undefined, meaning you cannot define it. When the x values are the same, that's what you get. Because that means that line is sitting right on some x value. X value is the same for every point on the line. That line's going straight up and down. 0 is your perpendicular line to that. It's horizontal. It has no rise whatsoever. So your 0 number is going to be in the top. All the y values are the same. So here's an example of 2 points. Don't worry about trying to graph this. What I want you to do is to take that, I'm going to pause this for a minute here, take that slope formula see if you can do the calculation to come up with the actual slope for this line. I'm talking about reducing fractions here with that problem. It's especially important once we start graphing these, because think about what 25 actually means on a graph. That means we got to rise 25 squares on the graph. And then we got to run 15. Lower numbers shrinks down the size of your graph. And that's a good thing. And so if you're wondering why I said 5/3 and not -5/3, it's because we got the same issue again with the signs. Same sign positive. That's the rule. So what I want to emphasize here, I'll do the calculation a couple different ways. So there's the top part of that. And the bottom is -6 minus 9. So there's my rise on top, the runs on the bottom.
You said it doesn't matter what order the numbers go, right? As long as you write one is on bottom.
Right. You know, I'm gonna demonstrate that right here. So if I saw the first point as the 9,11 point, that's one thing. But it doesn't matter which one you say is which. See, here's my fraction with the big numbers. Both of those end in 5, so I know automatically that they're both divisible by 5. I can reduce those. I got a negative divided by a negative, automatically makes it positive. So my end number is 5/3. Now, what if I did it the other way? 11 minus -14. And -6 minus 9. No, 9 minus -6. 9 minus -6. A lot of minus signs in there. They all supposed to be there? Yeah, they are actually. Because in both of these, this first minus sign is actually from the formula. The second minus sign is because of the fact that both of those numbers that follow it are negative numbers. A minus sign in front of 14, a minus sign in front of 6. When I substitute those numbers into the formula, I have to take their signs in with them. Which is kind of nice in this case because this becomes keep, change, change. So 11 plus 14 is 25. Same here on the bottom, 9 plus 6 is 15. No more minus signs. Get the same answer no matter which one of these points you say is the first one or which one you say is the second one. But when I did that first example and I drew those boxes, I did that to emphasize that minus sign in the middle as part of the equation. So you can't leave that out. You can't just stick -6 in there and be done with it. Because if I just put in this second one, if I put 9 minus 6 or 11 minus 14, I'm going to get all the wrong answers. I can't leave out any signs. Any equation like this where you've got to do some substitution with values, you got to take them in with the signs. So if it helps you to draw these things out like this, where you know, create little boxes to put the numbers in, if it's more clear that way, then that's what you need to do. All right, so that wasn't too bad actually, you guys. So questions, anybody? All right, we just had somebody else join. Okay, back to the show. Slope through these 2 points. 5 minus 0, negative 18 minus 17, minus. That's going to be keep, change. That time I used the first point as the second one in the formula. Again, it doesn't matter. 5 minus 0 is 5. That's my change in y. Negative 18 minus negative 17. That makes the 17 positive. So I'm going to get 5 over negative 1. And this is another bit of a tricky thing about the slopes that I want to emphasize. And I'll show you with the numbers so it'll maybe make more sense. The bottom line on these kind of problems, if either one of your numbers is negative, the slope is negative. Doesn't matter which one. So negative 18 minus negative 17. Oops. Negative 18 minus negative 17. I get misplaced there. There we go. So 5 minus 0 is 5. This becomes keep, change. Negative 18 plus 17, negative 1. So if I'm going to write the slope for that particular one with those 2 points, the slope is actually negative 5. Now, what if I did it the other way? And I'm doing this, I said it this way on purpose. So negative 17 minus negative 18. Did it again. I forgot a minus sign. See, there I go. My own worst enemy. Now I'm going to get positive 5 on the top. This becomes my keep, change. I forgot another minus sign. Negative 17 plus 18 now gives me and that should be negative 5. There we go. That gives me positive 1. I paused for a minute because, wait a minute, I'm supposed to be getting one of these numbers as negative. Should have been the first one on the top, 0 minus 5. I should have written negative 5 there. And so when I changed the order, it just made the x values on one be negative, changed it the other way, and made the y value end up negative. It's the same line. Those 2 points are on that line together. The slope is going to be negative because I got one of the values to come out as a negative number. If they're both negative or both positive, then it's a positive slope. And why is that? Well, it goes back to the rules that we talked about from day one about integers. I mean, these are division problems, right? So we follow the rules for integers for division. Same sign positive, different sign negative. Since we're talking about fractions here, these are division problems. So in either case, I'm still going to write the slope as negative 5 because I got a negative number for one of the calculations. The big thing to remember in all these calculations, be consistent. Don't take the first number from one and the second number from the other. Don't mix up the x and the y on the top and the bottom. There's a lot of different ways to mess this up. But if you just stick to the formula and put the numbers in where the formula tells you to, and don't leave out any signs, you'll be fine. It'll be easy to do these calculations. Questions on that, anybody? All right. tell you guys are just really excited about this today. What's our takeaways? Slope of a straight line. That's all we're going to be working with. Thank goodness. Next term, Algebra 1B, you'll start looking at some parabolas and curve shapes. We don't have to worry about that. We are talking about linear equations. Look at the word linear. L-I-N-E. It's right in the word. Linear equations are equations of a straight line. These equations have a constant slope. That's why when I saw those numbers in that table, I went from 1 to 2 to 3 to 4 to 5 to make sure it was consistent. Same change each time from one value down to the next. And the end result of all that, when it is consistent, when it's constant, is that the distance between the slope between any 2 points on the line is going to be the same. It has to be, or it's not a straight line. Of course, like we were just calculating, the sign of the slope is going to determine whether the slope is positive or negative. And that's going to tell you which direction the line's going when you have to actually put it on a graph. Very helpful. The steepness or flatness depends on whether the slope is a whole number or a fraction. Well, fractions are getting closer and closer to zero, right? It's less than 1. A fraction is less than 1. We know that a zero slope line is perfectly flat. So when you see slopes that are in fractions, now I don't mean improper fractions. I mean like 1/8 or 1/2 or 1/5, 2/5. Those are getting closer and closer to zero. So those lines are going to be flatter, closer to horizontal. But if you have a slope of 6 or 8 or 10, those lines are going to basically almost be standing straight up. So whole numbers give you steep slopes. And here's what I was just saying. Fractions, relatively flat. Whole number slopes, relatively steep. And then the last two pieces there that will be helpful to remember. I have the screen down far enough. The one that can't see in the class is the horizontal line slope is 0. So right there in those 4 situations with the positives and negatives, we've talked about all the different types of slope. Positive, negative, 0, undefined. That's all there is. Questions, anybody? All right, you got it licked. I can tell. All right, now comes the really fun stuff. Anybody here like to relax with coloring books at home? Adult coloring books? There's nothing wrong with that. I'm not trying to call anybody out. You should see all the pencils and pens that my fiance has sitting next to her chair at home. It's ridiculous. And she keeps buying more, but it helps her relax. The reason I ask that is if you like to do that kind of stuff, you like drawing, well, then maybe the graphing and drawing slopes is going to be for you. And here's where it all starts. Slope intercept form, the easy one. It's the easiest of the ones that we are given to work with for straight lines. Slope intercept here under example 1. What's the slope on that one? Well, all you got to do is look and see where the number is that's in the position where M normally goes. Yes, there it is, 2. Slope is 2. 2 over 1. If you want to say rise and run, you can take any whole number. You guys have heard me say this before. Any whole number, put it over 1, make it look like a fraction. Now you got the rise and run. For the y-intercept, it's the remaining piece here. That's the b. This is y equals mx plus b. Right there in the equation is m. That's the slope. B is the y-intercept. That right now is the only point that we know for certain is on that line. Sometimes we'll say for our graphing that B is for beginning. That's where we start. That's the one place that we know we can go. So if we went to this spot here, -1 on our graph and put a point down, what we're going to do is take that slope and use it to plot another point. And we could do that over and over and over again. Every one of those, since we have a constant slope, every time we do that, we're going to make things look more and more like a straight line. We only need 2 points for a straight line, but the more points you put on the graph, the easier it's going to be to visualize that. So that's the first example. The second example, that one's in standard form. 2x plus y equals 7. And we want it to be in slope intercept. Standard form does not have the slope. It does not have a y-intercept. There are other things that we can do with standard form to find some points. Maybe we can find the intercepts by doing some calculating. But the easy thing that works every single time is to convert it to y equals mx plus b. So solve for y. This is why we've been doing these literal equations, so that we can solve these standard form equations and get y by itself, and then they become slope intercept equations. This example 2 is an easy one because I'm going to subtract 2x from both sides, which is what they do. They're showing that down here, typed in. This is in your handouts too, in the materials, by the way, so you can download this or look at it yourself. And so that one, we only had to do one thing, and now we got y equals -2x plus 7. So there's our y-intercept, and there's our slope, -2. The last two examples, those are also in standard form. A little bit more work. We're going to subtract 3x for an example 3 on both sides. That's what they're doing down here. Normally for me, I'm going to stack them up because 3x minus 3x cancels. That's why we do it. If we're trying to get rid of something on one side, we got to be able to cancel it with its opposite. That's that zero pair we talked about probably in day 1 with our definitions. And then the last step is dividing everything by -2. On example 3, you see that we end up with a fractional slope. It's an improper fraction. I don't care. Don't put that in the calculator. Don't try to figure out what 3 divided by 2 is, because that's 1.5. Decimal form slopes do not help you graph. We need to leave it in fraction form, 3/2, because the top number is your rise, the bottom number is your run. So here's the examples actually put onto a graph. Here's that first example, y equals 2x minus 1. I know the y-intercept because that's what b tells me in the equation form. So I can put a point on the y-axis, not on the x-axis, not anywhere else on the graph. It is on the y-axis at -1. And what the y-intercept means is when x is 0, What happens to that 2x? 2 times 0 is 0. It gives you the value of 0, -1, because now y is -1. After that, I'm going to take the slope of 2 over 1. 2 over 1. Put another point here. Up 2 more over 1. Up 2 over 1. That you get that stair step effect. All of those little steps should look exactly alike. If I've done it correctly. Now, I don't know if I can draw a straight line here. Or no, that's not too bad. But the end piece on each one of those is the point that I placed on the graph. Because I went up 2, rise 2. Remember, put that 2 over 1 if you need to remember the bottom number as your run. And then I got a straight line. And if you're not sure, go do it on once you got the line on here. Up 2 over 1 should be on the line. Up 2 over 1 on the line. Up 2 over 1. Because remember, every point on the line is a solution to that equation. So we could take any 2 points, plug them in to the x and the y, and we're going to get a true statement. Questions? Anybody? Okay, here's the next 3 examples. Example 2, didn't have to change anything on that one. The thing that is shown here, where it says down 2 to the right 1. What if I went up 2? Which direction do I need to go then? Keep in mind, when we go up, it's positive. When we go to the right, it's positive. When we go down or to the left, it's negative. So if I'm going down and right, now I have my signs mixed, right? I got a negative and a positive. Down is negative, right's positive. Well, if I reverse that, up to left 1, I'm still going to end on the line. Up to left 1. And I can do that as many times as I want, and I'll still be on the line. Well, it doesn't matter which direction you go, but you've got to be consistent. And the reason I mention that is because what if you have a y-intercept that's way up here at the top of the graph and your slope is -8? Are you going to be able to go up 8 more? You're going to be off the graph. You don't have enough room. So you got to remember where you place that second point. The second point that you put on the graph is actually going to determine whether you've got the graph going in the correct direction or not. Because like from here with the +7 as my y-intercept, if I went down 2 and to the left 1, now which direction is my line going to go? It's going to go in a positive direction. It'll be going the wrong way because this is a negative slope. That's why I keep talking so much about up to the left is negative. Up to the right is positive. It's real. I feel it's really important to get a good visual before you even start graphing these things. I want you to think about, okay, I got a negative slope line. What should this graph look like? It's going to go up to the left before you even put anything on the paper. Because that right there is a check that you can use on your own work to make sure you're going the correct direction. Because this, getting these graphed in the wrong direction is about as common as forgetting a minus sign in a regular calculation. Happens all the time. So visualizing where they should go might help you with this. And you can see from examples 3 and 4, both of these are positive slope. They're both going to go up and to the right. why in my mind, I'm thinking that this one's going this way. The other one's going that way. This one, example 2, is going up to the left, but this got negative slope. I don't care about where it's going down below X, the X-axis. I'm just going to ignore all this down here. I don't care about any of that. When I'm thinking about direction, I'm only looking at where it's going to the top part of the graph, up and out. It just makes it simpler. Questions, anybody? That's basically how we graph in slope intercept form. Oops. Wow, this is different. All right, I want to look at a few more examples here. And if we were all in class together, we would have a bunch of these. I would do a bunch of them on the board. Then you guys would sit and do a bunch more. I'd come around and look at them. And hopefully by the end of the day, we'd have a pretty good handle on what this graphing is all about. Now, there's some things on this particular handout that are, I think, really, really good to use for example. And they're on here for that specific reason. If you look at the first two problems, those are both in slope intercept, right? Y equals mx plus b. Y equals mx plus b. What's the slope on number 2? Number 2 equation says y equals negative x plus 5. So what's the slope on that one? What does it mean when we have no number in front of a variable?
-1.
-1. Thank you. Excellent. Very good. That's what I was looking for. So that's one thing for sure you got to be aware of. Anytime you see, if that was just x, it would be a +1. This is negative x or minus x, so that means it's -1. So right away, before I do anything else, in my mind, I know this graph is going to go that direction. And this one is a straight stair step because I'm up here at +5. There's up 1 over 1 to the left, down 1 over 1, down 1 over 1, down 1 over 1. I'm moving 1 square at a time up or down and over or left. Gives me that straight line. There's your graph for number 2. The first one is one of these examples where I was talking about with you're near the top of the graph, the slope is -8. Okay, I'm going to try to estimate. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8 way up here and put a point somewhere. Nah. Nope. And this is also where I got to remember this line should end up going in that direction because it's negative slope. So I'm going to go down 8. And then I got a decision to make. 1, 2, 3, 4, 5, 6, 7, 8. Which way should I go now to place the next point? I got to go this way to the right. Very steep line. Up to the left. If I put that point over here on the other side, the line's going to go the wrong direction. Questions, anybody? All right, now number 3. Yeah. What's the y-intercept? Anybody see a number where B is supposed to go? This equation just says y equals 2x. Where's B? And so what does that tell you? 0. It is on 0. That's exactly right. Thank you. Very good, Jessica. And that's another one of these little quirks about the graphing that's really important to remember. If you don't see a number where B is supposed to go, normally that tells you that the y-intercept is actually at 0, 0. Because it doesn't make sense. It wouldn't make sense to actually write 2x plus 0. What does that do? It doesn't do anything. You add 0, it doesn't change anything. So why even bother? Nobody in math is going to do that. But it can be confusing if you're not sure where to start. So from there, though, it's just like all these others. I'm going to go up 2 over 1. Another spot there, up 2 over 1. This one's a positive slope line, so I'm looking for it to go up to the right. Down 2 over 1 the other way. As many of those points on there as you need to plot to be able to see where that line's going. Questions, anybody? Now, what do you notice about problem number 4 here? Yes, x equals -4. You could. Doesn't really help you, though. What happened to y? Where's y? Yeah. So if there's no y in the equation, what does that tell you about this line? It's also 0. The slope is 0 because I'll write this equation, y equals mx plus b. If the slope, if my value for m equals 0, oops, 0x plus b, what do I got? I got 0. Well, what if it's the opposite here? I don't even have I don't even have anything against the y. So the first thing that you got to do is figure out where this is on the graph. Where's your starting point? Well, only thing you have to work with is says x is -4. So here I'm on the x-axis, 1, 2, 3, 4. Okay. Where else is x equal -4? Well, it's -4 up here. It's -4 here. -4 down here. Every point on this line has an x value of -4. It's one of these specialty lines. Undefined slope. Because that equation is not even in slope intercept form. The other thing that you'll see, does this have it on here? Yes. It's not one I was hoping. But every undefined line is going to look like this. It's going to, shoot, didn't want that. It's going to start with x equals something. The horizontal lines are all going to start with y equals something. Questions, anybody? There's y equals x. If you look at number 9, y equals x. Okay, well, 0, 0, y equals x. So if y is -1, x is -1. If y is 1, x is 1. This is actually y equals 1x plus 0. That's kind of an exception to what I just said about why these horizontal lines starting with y equals something. Well, the something's got to be a number. So we need to be able to go somewhere on the y-axis and place a point, but we don't have that ability right now with that particular problem because it says y equals 1x. We do actually have a slope. Look at number 12. The funny looking slope, -9/4. Rise and run, no, they all work the same. It's negative, so it's going that direction. Starting at +4, that's our beginning point. Again, same thing as before. I can't go up 9, I'm off the graph. But I can go down 9, and I know that my other point's got to end up in that quadrant somewhere in order for that line to go the correct direction. Not over here. So down 9. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now over 4, 1, 2, 3, 4. Again, very common mistake to place that second point over in here. So I'm bringing that up as another reason or another example of a situation to try to do that visualizing before you even start doing the graph. Questions, anybody? All right, I got a couple more minutes here. So far, all I've done have been working with slope-intercept equations. There are other examples in your classwork materials to check out for practice. But when you get the standard form, that's what this handout is for. Get the standard form, it's a little bit different. Because, again, no slope, no y-intercept. You don't really even know where these lines are at, what they're doing on the graph. There's two different things you can do. We can convert them. So this first one here, 4x plus y equals 0. If I'm going to solve that equation for y, what do I do first? Subtract 4x, very good. Minus 4x from both sides. Minus 4x. So now I got an equation. And for the time being, I'm even going to leave the 0 there because that's going to remind me that that's my starting point. That's my y-intercept. That's an easy conversion. And if you looked at that at first and you thought, oh, okay, well, this is a 4x, this is positive, this line's going to be positive. And that's the problem with standard form. You don't really know until you do the conversion. So now we've done that and we got a starting point of 0. I'm going to go up 4 and 1 to the left. Boom, you got the line. Problem number 2, have to do the same thing. That's problem number 2 is going to take you 2 steps though to get to the final slope-intercept equation. A lot of them are going to be like that. Subtract the 10x first. Oh, that's hurting my fingers. So then I end up with negative 3y equals negative 10x minus 15. And I always put that, when I'm doing the conversion, I always put the x term right in after the equal sign, because that's the way it is in slope intercept. Y equals mx plus b. So I want my x term where the mx normally goes. Now all I got to do is divide by negative 3. I got to get to 1y. So negative 3 divided by negative 3 is going to give me 1y. So every term divided by negative 3. And voila, all the signs are going to change. Y equals 10/3 x plus 5. Okay. Again, I'm at the top of the graph though. There's my y-intercept now that I figured that plus 5 out. 10/3 is a rise of 10. If I wrote it traditional fraction, rise of 10, run of 3. It's a positive slope line now, so it's got to go that direction. So down 10 all the way to negative 5/3 this way. Can't draw a straight line with this thing to save my life. I suppose if I had to, I probably could, but. So there's a bunch of different standard form equations in here like that for practice. And look at what you got here. You got the answers. This is in here for like some of the other handouts, like when we were doing the inequalities and doing those graphs. Give you something to reference, check your work. Here's one of these in problem number 9. This is one of these horizontal lines. Y equals 5. Every point on that line says y equals 5. They use all the x values, but only one y value. That's how you know it's a flat horizontal line, because if you did the comparison, change in y, well, it's always going to be 5 minus 5, no matter where you're at on that line, because the y values are the same. Questions, anybody? Kind of rushed through that a little bit. It's not letting me get to that for some reason. There is a handout in here that walks you through the conversion from standard form to slope intercept step by step. So if you need to, there's lots of extra practice in here also. So if you want my feedback, this would probably be a good one to do some of those calculations on. Take a picture of it, send it to me. Say, hey, am I doing this correctly? Be happy to do that. So all of those are in this part of the materials under forms of lines. And Thursday, we will move to the last of the 3 forms of lines, point slope. Don't worry about that one for the time being. We will do that on Thursday. Yeah. No, there's a ticket in on it. There's stuff for them. I don't know what they want to do. So, yeah, thanks. Oops. So here's another one of these graphing this one's in slope intercept. All these are in slope intercept. And the second page here of this particular handout is actually one where you have to find the intercepts. We'll do some of those on Thursday also. It's another calculation. Sometimes it works when you have numbers that are factors of each other, but it doesn't always work with standard form. So any questions, anybody? All right, we are at the stopping time pretty much. I'll be available tomorrow. If you got questions on anything, please let me know. Send me a text. Hopefully I'll be back in business with not my personal computer by Thursday. Boy, Steve stopped in, so. Are you guys all in shock here in the classroom or what? You guys all just kind of paralyzed? Okay, cool, great. People are getting it. So I can let everybody else at home go, and we'll see y'all Thursday.
Okay, thank you.
All right, thank you.